possibility anyway. Let me get started. It's now 10 o'clock, and you all should be able to see the title and a photograph to sort of exemplify the title, and a definition of what geothermal is, and then a question at the end, which is the most important part. Shall we increase it? Now, this picture, many of you might recognize from other photographs or for having visited Iceland. This is the Blue Lagoon in Iceland, and you can see people enjoying the beautiful warm water, standing in little clusters. These are tourists, and every little cluster has its own little group of friends and language. And I found when I was there that you could sort of drift from one cluster to another and pick up or overhear different languages, Asian languages, European languages, all kinds, and it made it kind of fun. This picture I didn't take. This was taken from a no, I'm getting a little distracted here. This was taken from a some sort of a drone, I would guess, because it's a nice elevation and it shows behind the swimmers, or the you're not really swimming very much. You're just sort of waiting around, enjoying the lovely temperature. But in the background is the geothermal plant. And Iceland is unique. There are a lot of geothermal energy all over the world, but it is unique in the amount of geothermal energy per person and what the many uses they put it to. So it's sort of an interesting beginning. So let me move on to the next slide, if I can get the slides to work. I think they're down here. That's right. Yeah, here's a little basic idea. There is obviously heat flow from the depths of the planet, and the heat is generated by the decay of radioactive elements in the crust. Most of us are aware that there's uranium and thorium down there in the center of the planet, but there's also a lot of potassium. Now, potassium has an atomic weight of, 39 in most of it, but there are other isotopes of potassium, particularly potassium-40. It's only 0.1% of all the potassium on the planet, but there's enough there to be contributing significantly, along with the uranium and thorium, as it decays, to heat in the core of the planet. So that's one source, and the other source is the upward convection and conduction from the Earth's mantle and core that's there already. So you have a steady state of pre-existing heat in the center of the planet, and then more heat being generated by these radioactive elements that are decaying. You can see in the image to the right the cracks in the rock, allowing any water that's there to permeate up and to turn turbines, have a safety heat exhaust, and some reservoir for injecting back in. A little more detail in the next slide. Gives a little more background. This is from a popular site called Tree Hugger. And they break it into 4 sections here. First, you have on the left the schematic of the planet with its interior core. And then that allows you to look more centrally to see that there's a reservoir, oftentimes, of water or fluids, salts, various things like that, that are near the surface. This reservoir is heated up by heat conducted through the rock. And then you can see an up arrow here that allows some of that to go up into a hot water tank. The steam generated turns a turbine and makes electricity. And you notice there's there's a return pathway to a cooling tower and also allowing some return to the reservoir. So it adds a little more complication. People are now trying, particularly in Germany, to simplify this and make it a closed loop system and eliminate some of these reservoirs. And they find that they can make it even more efficient, simplify it, reduce cost. So I'm going through about 3 or 4 slides here, ranking geothermal in different ways. This slide is very interesting in that it ranks geothermal by individual plants. And it's just a couple of years old, so it's fairly January 2021, fairly current. And the largest plant in the world is the geysers right here near Santa Rosa, California. And that's 900 megawatts. To put it into familiarity for you, that's similar to a nuclear reactor. Nuclear reactors, some of them are less than 1,000 megawatts. Some of them go up to 1,200, 1,300, and so on. So this is in the ballpark of a nuclear reactor. Most of these plants are much smaller than that, and the average size is smaller. But these are some other ones. I think it's interesting that Italy is the one that's listed second. They beat us in making the world's first geothermal plant over 100 years ago to power a railway system in Italy, and that's still operating. It's Larderello, and almost as productive as the one in the geysers. I will show you quite a few slides from the geysers later, so we'll get back to that. Then they come in various sizes. There's big ones in Mexico, Philippines, Iceland, you just saw a picture of, Philippines. Then there's the Salton Sea. We'll touch briefly on that. Southern California, near Palm Springs, California. And then Philippines and Indonesia have some more there, various sizes. We're going to change our perspective now and go from individual geothermal plants to how countries rank. And this is in a sort of a semicircular table. Again, US comes out on top, with Indonesia following, Philippines and Turkey, followed by New Zealand and so on. But after New Zealand, they're no longer in that 1 gigawatt country club. This is a gigawatt, of course, is 1,000 megawatts. So anything over 1,000 megawatts would be a gigawatt. And so in this capacity here, you just have to put a period where the comma is, and you have the number of gigawatts, and you add them all up. And the total is about 16 gigawatts for the entire planet, and various other countries. And you see that Iceland here is a little small country, and therefore is way down the list, even though they take advantage of it on a per person aspect much more than we do. Interesting way to look at it. There are many different interesting ways to look at it. This is the American contributions are mostly out west, especially the Southwest. California is by far and above the biggest contributor to geothermal energy. And you see in the white letters, those are the current levels in megawatts. And the yellow is what their plans are. So California has 2,700 megawatts of geothermal energy, and they're planning another 800. Nevada, a close second, also doing well. The other states, not so well. but even Alaska and Hawaii contribute some geothermal energy. The prevailing views about the future of geothermal are that we could do much more. Some people raise the question of maybe we could increase it 50-fold. Up in the top paragraph there, I pointed out that even with this 3,700 megawatts, which this all totals to, that's only less than half of 1% of all the electricity sources in this country. And because it is clean, relatively clean, and doesn't emit CO2 to significant degrees or methane, it's considered an important renewable source, but people don't pay a lot of attention to it because it's only a half of 1% of all of our electricity sources. But if you could raise that 50-fold, then you could get up into meaningful levels of 10% or so, excuse me, which would be equivalent to getting close to what we do with nuclear energy. They say we might be able to accomplish this by drilling more deeply. We'll get into the depths, but typically we tend to dig down, or drill down, I should say, about a mile, about 5,000 feet or so. Most of the people talk it in meters, which of course makes more sense. And so they're talking about 350 to 400 meters. And they think if they drilled more deeply and then injected rock layers with special fluids that permeate the rock, that would help. And I think it would. You have to worry a bit about what these special fluids are and make sure they're nothing like the ones that were used for drilling for oil. Another approach was used in Santa Rosa, and I'll talk about that in a little while. So Santa Rosa is right there. If you can see my pointer, just directly across from Lake Tahoe, north of a little distance, about 100 miles north of San Francisco. And it's a special place and by far the largest production of geothermal energy in the United States. If we go back the slide, we see this guy acknowledged, Billy Roberts. And the data is kind of old. And so I thought maybe I should look and see what he's done more recently. So when I did that, I found this map. I call it Billy's newer map. And I find that Billy is supported by and takes data from the National Renewable Energy, trying to think what the L stands for, I've forgotten. League or something like that. And while it is more current, it doesn't have a date here, it does show more detail in terms of the orange and the yellow spots that are currently where plants are located. So the orange would be a region that's hot, and Colorado, for example, has some regions they only have 4 plants, but they it gives a little more detail than the previous slide.
Richard, if I could just, NREL stands. This is Lou.
I hear.
You hear me?
I can barely hear you. Pick up again.
This is Lou. I don't know why I'm not louder, but I'm right up there.
That's okay. I hear you now clearly.
It's NREL is National Renewable Energy Laboratory. It's one of the 17 laboratory. It's one of the 17 DOE labs. They do they do a lot of different work with renewables.
Yeah.
Anyway, the question I might have is the frac. Is this proposed 50 times more energy using fracking? Is fracking part of the deal?
They would say no. And there's good evidence to support that, but I can't speak for the industry. They do not want to use definitely the same chemicals that fracking uses because they don't need to. If you get down deep enough and recirculate the water down, there's no need to separate the layers. separating the layers was for getting the oil and gas out of the deposits of fossil fuels. You don't need to do that for geothermal. You simply circulate the water that you put down. Sometimes there's a natural reservoir, sometimes not. Most of the time, people have been using natural reservoirs that are largely water. So they would deny it strongly, and I think in general, they're right. There might be a few instances where they generate a few earthquakes, small earthquakes, as fracking does for various reasons, where you can disrupt the volumes down there, but I would not associate it with fracking. To answer your question, thank you for the definition of lab. I should have remembered that. I'll show you some slides from NREL right at the end of the talk, and it blows me away because NREL is thought to be a government organization, and it is. There are about, I think, 800 workers there, and about half of them, however, are from a league of environmentalists, strong environmental leaning, and therefore I find their data often quite biased in favor of environmental things. We'll see that near the end of the talk, but thank you for your good question, Lou. It's right on target. Okay. Okay, get my arrow here. This is an interesting statistic. Global leaders in geothermal energy. If you use the population and think in terms of megawatts per population or terajoules per year per population, where you have the time element as well, you notice that Iceland is head and shoulders more of a leader when you take into account population, particularly over time. Sweden, Finland, Norway, and Switzerland are down the list, and the others, of course, much lower. So it just shows that Iceland, while a small country, they sure take advantage of thermal energy. It's a natural gift for them, and they know how to utilize it very well. I'll show you some slides of that later on when we get to Iceland in detail. Just a global distribution of geothermal energy is enough to look at the United States, but we need to look more broadly. There's a fair amount in Mexico, a tiny bit in the Caribbean, in Chile, lots more in, you notice this, the Ring of Fire, we call it, around the Pacific Ocean, aside from a little bit in Hawaii. Most of it is rimming the Pacific, and then, of course, some sites here in Kenya. We'll talk about that later, and through some of these mountainous regions of Europe and over to Iceland. So that shows you a global perspective. It has importance, and I think what some of the proponents are saying is that we could enlarge that considerably with good drilling. We'll come to that later. Just so we don't get focused entirely. Yes.
Going back to the last slide, if you could.
Yep.
It seems that the geothermal usage is pretty much along the plate lines for the interfaces, both in Europe and, you know, Japan and the US.
Right.
That may restrict the capability to expand geothermal beyond those regions.
I think so. But it's, if you go back, maybe let me try that, several slides there. You see that the United States is a pretty varied region, and all our plants are in deep orange or orangey brown. And that could be expanded quite a bit if we could use closed loop. That is where you don't have to re-inject water and make them more efficient and dig them deeper. You might be able to broaden both the distribution and the effectiveness of them. So I agree with you. I don't expect to see any big geothermal plants in Wisconsin in the near future, but certainly you could develop, considering the fact that it's there's no radioactivity to scare the public, no threat of bombs, so on. We could certainly expand. 50-fold, I think, is a reasonable estimate. That's a lot of plants, but they're not necessarily terribly expensive, and I think that you could expand it. But I agree with you. They're certainly not. Don't expect to find them in India or large parts of Africa or Australia. So you're right. It's limited still. But the point made by many people is that it could be enhanced a lot more than it is.
I'm not against that. I'm just observing that even when we go to the U.S., where you showed all the geothermal, the overlap of our population is way east of the Rockies.
Yeah.
And even in that area, the coastal California up to Seattle is the concentration of people in industry.
Yeah, you're quite right. No argument there. I'm having problems with my pointer here. It's gone fluey. Hang on. I can't. Oh, there. I've got it now somehow or other. Okay. Yeah, your point's well taken. Only so much. When they said 50-fold, they're still talking 10% or 5%. So we're not talking 90% or anything like that. So things that we've learned from various countries and states, you can, in the Netherlands, for example, they grow plants in geothermal sources and greenhouses. Centrally here, you can, they certainly heat homes, especially in Iceland and in Oregon, the state of Oregon. They put pipes, geothermal pipes underneath roads and runways to heat and avoid all the problems of plowing and salting and so on of roads in the wintertime, get the snow off. So there are other sources as well. Also, global construction, again, thinking globally, has been stable over the past 15 years or so. At least that's the data that we have total. It goes from 2010 to 2025. But look at the most active countries. It's not an even global thing. Indonesia and Turkey are the two most actively getting involved. We're doing a bit. And Kenya, we'll talk about that later, why Kenya is so excited about it these days. Okay, coming to the Geysers project in Santa Rosa. The Geysers is up here. Unfortunately, it's obstructed a little bit by, yeah, there we are. There we are, there, that red dot. And there's pump stations at these other little red dots. But what they found back in 1987, this was drilled 100 years ago. So it was not long after Italy that they found these steam fields, and they started to harvest them, take advantage. But they saw that by 1987, probably been going about 65, 75 years, it was peaking, and they were losing some of their water from steam, and they weren't re-injecting it very efficiently, and they were afraid they were going to lose their energy. So they started having a meeting in the late 80s, and it took them about 10 years to agree. But by the turn of the century, around 2000, they had a plan, and they built this $187 million, 41-mile green pipeline here that went from Santa Rosa, and it's not just the center of the town here, it's from their recycled water. They're so-called treated water. And it also does provide some irrigation along the way. I'll show you some details of this. My son is a vibrational analyst engineer for GE, and he was recruited to come and help some of the vibration in the turbines, and he was able to provide some of the data here that I'm about to show you. So we'll come to that. The original geysers had developed some issues. Only 20% of the steam was cost effectively put back into the ground, and the resource was slowly depleting. This is sort of a picture of the simplified picture. They recaptured some of the steam, but not all of it, and so they were losing some. And so they began working, as I say, around 2000 was when the first pipeline was put in after a lot of planning, and they were able to build it mostly in 3 years. There were 9 construction companies, and it took over 700 people. Here's a guy inside a pipe welding away. Here's a pipeline going into a trench, and here's a cross section of its installation. This is kind of interesting. The schematic representation of this pipeline. If you look along the bottom of the slide here, you can see the countryside, Santa Rosa, the extreme left, lower left corner, and then you can see the line extending 41 miles, and you can see it's coming up over a rise here. And then when you schematically portray it, it reveals in easier to follow manner the 17 isolation valves, smaller little ones that you see, and then the larger pump stations that are in black squares. Notice that there's some red arrows here. This is special isolation valves that close automatically if an earthquake happens. So in this region of California, they're not going to put in something like this unless it will take care of itself in an earthquake. And they successfully did that, at least successfully so far. It's been working well. So to summarize, they boosted their output by 85 megawatts and made it more resilient and self-maintaining by recovering their water and not losing it this way. So it worked out pretty well. Moving to the Southern California, Salton Sea is an interesting location, and it's undergoing a lot of natural degradation because it's been abused for so long. And it's sort of nice that this geothermal plant has been built here, I think, because it gives people who are very renewably conscious in California a rationale for taking care of the plant and taking care of the Salton Sea next door, for better care. So they feel it's only been about a quarter developed as much as it could be, and they're certainly put the electricity to good use in the Palm Springs area where they it's a very active tourist area, and lots of electricity is consumed there. So they think that this is another example of a good location in California. And Klamath Falls, Oregon, was the area where I mentioned that several commercial, nonprofit, and government facilities take advantage of this. They to melt snow on the sidewalks and bridges. There's a proximity of wells and heat exchangers right in the downtown area. And this is an example of a drilling operation that allows rejection of fluids back into the aquifer.
Richard, can I make a,
Just,
Richard, do you hear me?
I hear it very faintly, Lou. If you could
I'm gonna have to,
speak up a little bit more.
yeah.
I'm afraid I'm not hearing you. Try again.
Is this any better? No?
Slightly better.
Oh, what's going on? back to the Salton Sea, that area in California, there's a lot of reservoir underneath the ground. Obviously, that's typical of what you're talking about here. But that's a rich source of lithium. They're starting to harvest lithium from underground in that area. And it's just a sidebar. It's not related to this geothermal stuff, but it's another thing that areas could be valuable for. Okay, that's it.
Thank you.
That's it.
Yeah, thank you, Lou, for mentioning that. I do appreciate it. It was something that slipped my mind. I had thought of that and didn't put it in, but it's a very good point. And the lithium there might make people recognize the value of the area even more. So it is a sideline, but a side note worth taking and seriously thinking in terms of its future. So thank you for mentioning that. These two images I took when I was visiting Yellowstone.
Isn't there no sea left
Okay.
in Salton Sea?
Oh yeah, there's some left, but it's getting very saline. Some of the birds are finding it a little tough and they're migrating through there because it's so salty. The fish are having a hard time. It needs to, and it is losing in volume. It's not been managed very well, and I think given the lithium and given the energy, hopefully people will. The people are people who live around the lake are not all that well off. The poorest part of that whole complex live in the east side of La Quinta, and La Quinta is a very rich area. The PGA is there. And I think eventually the powers that be will take better care of the Salton Sea. But this is just, these are more the lithium and the geothermal energy add incentive to take care of a nice resource that they have.
Do they need water for injection to get steam out of that? Because
the water's underneath the soil line. The water is underneath.
Yes, that's right. But we don't want to deplete that either, Lou. That water they're using for their wells and their drinking water. So they would want to take good care of that. But they are sitting. Palm Springs is sitting on a very nice body of water. I'm trying to think of the name they use for it, but it's a precious resource, and they would want to be careful with that. But yeah, I don't have the answers. I'm sorry. I visited the area a number of times, but I don't have the details on what the planning is or what they're going to do with it. That would be for another time. If any of you guys would like to give a talk on it.
The reason I asked is I believe PBS had a scenario presentation on the Salton Sea area, one of their programs about a year ago.
60 minutes.
Showed a lot of abandonment area.
Well, that's another program, but 60 Minutes had one on the lithium. They pump the water up and then return it underground and pull the lithium out. Anyway, that's just getting started. It's not clear how much will go on with that.
I think you're right. I saw both programs, and they were programs that presented the dilemma, but no solutions yet that are very clearly defined and agreed. Yeah. Okay. Well, we're doing right along, pretty much on time here. Appreciate your interjections and questions and comments. I just threw this slide in, pictures I took about 6 years ago when I was out in the Yellowstone area at the time of the solar eclipse. What's seen on the left is not Old Faithful. That does come off pretty regularly, and it's over where it's located is just behind this big building here. And it doesn't happen to be going when I took that picture. This is just a fumarole. That is a little sideline. So the whole area of Yellowstone is sitting over a gigantic dome of hot rock and water. And this is an example of the conflict between tourists and industrialists. This was one of our earliest parks. There's no way that industry is going to be allowed into here. It may not even be very useful, but it's a beautiful area, has many other things attracting it besides Old Faithful. And so I just put it in because I'm going to show you some other countries where there's a conflict, a serious conflict between tourism and the industrialization of geothermal energy. And fortunately, we have enough space in this country, and these were made into parks back in the days of Roosevelt, Teddy Roosevelt, that there's no going back on these parks now. These are going to remain tourist attractions for the foreseeable future. But
until
so just
it
a
erupts.
comment that pardon?
Until it erupts.
Pardon?
The super volcano.
Right. Yeah. Yeah, people have talked about that, but they don't take it too seriously. But yeah, the word Yellowstone, by the way, comes from a name that the indigenous peoples of the area applied to the gravel, which picked up a yellow tone from some of the dissolved salts. So just to know the origin. Okay, now we're going to go abroad. I mentioned the second line in one of the earlier slides was this first plant built in 1913. It had a fair output of 250 megawatts, not bad. Built in Devil's Valley by Prince Kunti to power a railway, and it's the oldest geothermal plant in the world still running. It's now used I just threw this in on the side, now used in about 20 countries, and the world capacity is about 16 gigawatts. So that's a picture of it in the distance. You could see these domes don't necessarily mean it's nuclear. They're used around coal plants, geothermal plants, as well as nuclear plants to help with the drawing out of the steam that's not needed, and it's sort of a built-in control. Moving to Mexico, sorry, the slide is a bit out of focus, but it's in the Baja Peninsula, very close to Mexicali. It has an output of 820 megawatts, so it's the largest geothermal plant in Mexico and one of the world's largest. This one in the Philippines, Tonganan Field in Leyte Island, one of the larger Philippine islands, and it's the second largest producer of geothermal energy globally, they say. The operation details are poorly known. I think the Philippine Islands feel that they're close enough to Taiwan or other nations, perhaps, that we're getting some background noise. Be careful, please. The operation here is poorly known because of security concerns. Now we're back to Iceland, the Blue Lagoon. That picture I took back in 2007, I thoroughly enjoyed my visit there. It's at the top end of the Mid-Atlantic Ridge, and I'll show a picture of that in a minute. It makes a unique destination for tourism as well as heavy industries. They've got a large plant there for the refining aluminum from bauxite. And it's because the electricity is so inexpensive that it's a logical place for ships to bring in the bauxite and have it refined into high-grade aluminum. The next few slides will just show some other spas recently opened, but we do have a few more things to talk about Iceland here. Here's a picture of the plate margins, the Mid-Atlantic Ridge showing the Eurasian plate going off to the right and the American plate to the left. And you can see the outline of Iceland and this little sort of island that formed in the middle of the Mid-Atlantic Ridge. To the right, you see the areas that are high temperature in orange and low temperature. You remember there's a mountain there with ice on it. A fairly dormant volcano, but it does blow every now and again, and it did not too many years ago and left a lot of dust in the air for transatlantic flights to avoid. But it's a fascinating part of the world. I highly recommend it to any of you who might think about visiting. Iceland, it's easy to get to. If you're going to Scandinavia, you can fly Iceland Air and drop in en route and stay for a few days and enjoy it. On the lower left is some of their beautiful waterfalls. And on the lower right, something I don't highly recommend. I took a ship to Greenland from Iceland. And on the way back, we ran into 30-foot waves, had to buckle ourselves into our beds, and a little worried about the ship, but we got back, although it was a day late. The captain said his predecessor had been sent to Siberia for allowing his ship to capsize, so he was going to take special care not to let the ship flip over. So with that knowledge, I was able to get a fairly good night's sleep in spite of the bucking waves. So lots of adventure. You don't have to do that oceanic travel, but if you combine Iceland and Greenland, you might run into that. These are some new images, just came since I was there, where they have taken hot springs along the coast and just built them into the rock. And you can see this nice stairway and a doorway that lets you in, and you're right by the ocean. Another image like it. Seaside Icelandic lagoon, very, you don't like the blue lagoon and all the people in little groups, you can just enjoy a little more peace and tranquility at this spot. Okay, last slide about Iceland is really quite informative. Iceland is a pioneer at harvesting geothermal and uses it for 40% of its electricity, as shown here in the blue-gray. That's a lot. But they use 43% for space heating. When you go to Greenland, there are no advertising along the roads. It's very clean and tidy, but you will see sometimes some big ducts going along the roadside or overland, and that takes space heating to the homes in Reykjavik. They also use it for greenhouses, fish farming, industry, snow melting, and swimming pools. So a lot of different advantages. When I was there in 2007, they were talking about electrifying their fishing fleet because they had so much energy. Unfortunately, they ran into some financial problems around 2008, as the whole world did, and that plan didn't pan out. So they're still using fossil fuels for their boats, planes, and cars. In Indonesia, they have significant energy. These are just some pictures left and right of the piping used for to feed the water back into the plants. Japan sits on the third largest geothermal resources in the world, and this image shows these residences, like lovely little hotels, and then the industry over there of a geothermal plant, and that's causes a problem. 10% of Japan's electricity could be derived from these geothermal. It's domestically clean and renewable, but the owners of Japan's hot springs are powerful, and they fear the geothermal power plants will disrupt their precious tourist resources. So they have this industry, it's called onsen, which means powerful leisure. And not in my backyard, actions are blocking geothermal energy there. With over 100 active volcanoes, Japan has a potential resource equal to 23 nuclear reactors. I thought that was a fascinating statistic. They've shut down most of the reactors, and they're only slowly getting them back into operation after Fukushima 12 years ago. But they're heavily dependent on imported energy. They buy a lot of liquid natural gas and other sources of fossil fuels, and they've missed a huge opportunity, say some people, by allowing the tourist industry to, with 3,000 resorts attracting 130 million visitors per year, to block some of their geothermal potential. So it depends on your point of view. I mentioned Kenya before, that their new interest and in geothermal, it's because they have a rift valley that runs right through the country that allows for shallower wells about half as deep. So in other words, about a half a mile instead of a mile, or maybe even less than that. So it makes the highest share of any country's electricity in that region. They have a park there, Hell's Gate National Park. It provides 50% of their electricity. So that's sort of like Iceland in that regard. Kenya is the 7th top producer of any country on the planet because they're really working to harvest that energy from the Rift Valley. Hawaii
Richard?
has a plant in Puna. Yeah.
Question, Richard?
Question?
Yes.
Yeah.
Is that rift part of the separation of the tectonic plates in Africa that's causing the continent to split in two?
Yes, there's a north-south Rift Valley that goes through Kenya, and Victoria Falls and a number of areas are connected with that. But it is a north-south running valley that's very ancient and is part of the separation of plates. You're correct. So good question. Thank you. Hawaii has on the Big Island of a plant at 21 miles south of Hilo, and you can see this well here, and not quite sure what these represent, but in any case, this is a picture of the well and the lots and lots of pipes bringing the recirculating the fluids into the depths of the well and producing 30% of their electricity for that island. So that's pretty good. North Island in New Zealand, for any of you who have been to New Zealand, the North Island is much more volcanic. And Waikai, I guess it's pronounced, makes 20% of their electricity. So that's an example there of geothermal energy. Now, the last bit of my talk is going to be about enhanced geothermal systems, or EGS. Enhanced is a very important word to remember because you'll see it abbreviated. It's kind of 3 long words and people don't want to be bothered typing it out, but you'll see EGS very often in association with geothermal things today. It's the byword. So just take note for it because the vast majority of them now in modern approaches follow this EGS system. Basically, there are 3 steps. First of all, you have to find, assess, and develop a site. You have to drill into hot rock and inject enough hot water to create a reservoir. In most cases, there are exceptions to this that I'll come to later in Germany. Step 3 is to build and operate a plant and maintain its reservoir by recycling the water, and that's key. Otherwise, you'll, of course, run out. And you can see here in the diagram, the blue is, of course, representing the colder return of water to this site or reservoir, and the red are 3 lines carrying hot water up to the plant, and with the turbine generating electricity. So that's basically the concept in this illustration, with fluid injection enabling hot rock to become a geothermal resource.
Okay,
the idea is that rather than, I'll just be with you in a minute,
Yeah.
rather than wait for geothermal to show itself, you map for it and then you dig down into it. So you're creating a new spot. And that's the point that I've been leading to, and that we talked about why they think it can be raised 50-fold, is they think that there are a lot of places that are not spontaneously coming to the surface yet. But if we take those areas on the map that I pointed out that were orange and convert them into a plant like this, we can harvest a lot more energy than we presently do. Yeah, Lewis, were you there with a question?
Yeah, I am. Hopefully you can hear me okay. Yeah, at the very bottom, it looks like that area's been fracked. I thought I heard that in one of the PBS shows that they do fracking down here to create more air, more ways to transfer heat, from the cold back to the warm line, hot lines. And I think that is fracked at the bottom. I might be wrong.
That could be diagrammatic. It just says what's said down there is injected geothermal fluid and enhances the permeability of the rock. So I think
That's called fracking.
Yes, it is. That is fracking. Thank you, Stephen.
Yeah, but it doesn't mean you're putting in chemicals. It could
Right.
be that you're just putting in hot water, and there might be some chemicals, but I'm sure they're not using those ones that I guess they were made secret by our Vice President Cheney years ago, and it was never revealed what was actually in those chemicals. But they're not putting that stuff in here, I'm sure.
Well, I think if you're along a rift and utilizing the underground plate tectonic being pushed up by this hot area underneath, if you just inject water or salt water from the ocean, you're going to frack just because of the thermal change. The rock is going to expand, and the steam created down there is going to break up whatever it is.
You make a point. I'm not sure how you define fracking, and we think of it in a very negative way as in association with the fossil fuel industry. But if you broaden your definition of fracking to any injection of any fluid, then yeah, you would have to say it's fracking. I'm not sure how you define the word, but I think your point is well taken, because when you read about this stuff online, if you're not a geothermal engineer and you start reading about it, you find that while some of it is very, very positive, and they keep emphasizing the positive things about it, the fact remains, when you read a little more deeply, is that about half of these wells are abandoned because for one reason or another, they don't work the way that they predicted or hoped they would. Sometimes they're minor earthquakes. Other times they fill in with things they don't want. So it's not like every well turns into a wonderful enhanced geothermal system. But I'm going to show you some examples of where it's worked out well. And
there was a practice when wells were drilled just for water. You would drill a well down, and then you would put an explosive at the bottom, and that would break up the rocks so that you got water into the well. Now,
did you say an explosion?
Yes, they dropped dynamite down the well.
Wow. Okay. Do you know who did that, or was it widely done?
I think it was widely done.
Okay, I didn't read about that, but maybe they just chose not to publish it. It's not in these 3 steps. They don't say they say drill into hot rock and inject enough hot water to create a reservoir. They don't say send down some dynamite, but but it might be that they do it and they just didn't bother to put it in.
Yeah, I think you wouldn't want to drop down dynamite if you drill down into a layer of petroleum. You might get an underground fire that depletes your resource.
Right. Yeah, you blow up the whole place. That's true. Okay, let me show you the next slide. Might help a little bit. EGS then is defined for clarity in this 2-well system. You can see the 2 wells there, one with an arrow going down, the other with an arrow going up, a production well and an injection well. And it says the EGS would exclude high-grade hydrothermal hot springs, but it does include low permeability resources in sedimentary formations, as well as in geopressured magma and low-grade unproductive hydrothermal resources, as sketched here. It said it also might be co-produced hot water from oil and gas production as an unconventional enhanced geothermal system resource type that could be developed in the short term and possibly provide a first step to more classical EGS exploitation. So these are words from websites where I've tried to define it as best as I could, lifting their words, what EGS means, what it doesn't mean, and what it does include. But you'll see it a lot now when you see all the current things that they're doing. For example, there's a company in Texas, and it's really funny to read their system. It's called SAGE, I suppose named after the plant that's prevalent there. So they use that term. And these words are taken right off their website. If you're not one of the 500,000 people on an airplane or 10 astronauts in space at this moment, you are on top of a giant nuclear ball. There is a monstrous source of heat below us available wherever you come out a drill like this one. That's a bit over the top. Obviously, that doesn't apply to Wisconsin, but I think they're thinking of like a Texan, and probably there's a lot of it in Texas where you could do that sort of thing.
Well,
there are a couple of
Devil's Lake is a caldera.
It's pretty old, Devil's Lake. I don't know. I wouldn't count on it. But I really doubt it. But anyways, it's a thought. Tim Latimer is one of two guys involved with this company called Fervo. And it began 10 years ago when he was in the oil and gas industry as a drilling engineer. He loved the work, but he was passionate about climate change, saw all the tech advancement, and realized that it could be used for geothermal. And so he got a thing called GeoVision that I'm referring to here in the top line. I haven't researched that thoroughly, but apparently it's a computerized system that allows you to analyze future potentials. And when they did that, it's out there in the public. They found large energy resources that they didn't know were there otherwise. It provided grid flexibility, around the clock energy availability, and opportunities to an essential part of our nation's energy infrastructure. And I put in this little red note, wow, this sounds almost as good as fishing. However, and this is a caution, earthquakes and problems with drilling can lead to well abandonment. And in some cases, I think it can be up to 50%. But anyway, Jack is pretty excited about it. Here's a picture of him on the right with Jack Norbeck, and they're really happy with their work doing so far. This is a picture of some of their wells. They're way up, not just down in the south, they're up in northwest Nevada. These are deep wells, rapidly absorbs the earth heat at 375 degrees Fahrenheit. That's sure warm. The hot water is then pumped back to the surface for conversion into electricity. And Google apparently is invested in it. They expect to have a 400 megawatt project online within another 5 years. So then there's Ivor Loop technology in Bavaria, and they're collaborating with people in Alberta. I'm not exactly sure what Alberta is providing, but they must be providing, there's a lot of fossil fuel development in Alberta. There must be some good drilling technology. So there's some cooperation going on, but this is taking place. They use 12 kilometers of loop technology dug 4.5 kilometers deep, and they develop 8.2 megawatts. Again, that's equivalent to a very small nuclear reactor, but it's clean, and of course, so is nuclear. But people aren't so scared of it. In Germany, they won't hear you talk about anything nuclear, so at least they can get away with developing this system. They're quite happy with this loop because it's they can avoid building a reservoir. They can don't have to re-inject if they have a closed loop system going, and they say that they've simplified the technology so much that they feel they can produce energy for Bavaria in a very efficient way. And they're considering they don't have so much, if any, oil coming in through Russia, they're really happy to have this source of geothermal energy. And,
just a note. I don't see any cooling towers with this one. Maybe that's why it's simplified. There's no
Correct.
cooling tower.
Correct.
You probably would with the bigger ones at least.
Yeah.
And
I think
possibly
Another question.
Yeah.
It says 12 kilometers of loop technology. If it goes down 4.5 kilometers, that's already 9. How did they get the other 3?
I think the other 3 are branches. It's like an inverted tree. So they have a vertical depth of 4 kilometers, and then they have many branches coming out in all directions at different levels. So that's how they get to 12. Okay.
And just to go back kind of to the last question, fracking, there is a new technology, and that is they insert a special drill into the ground where the rock shale is. The drill releases microwave frequencies, roughly the equivalent of 500 household microwave ovens into the earth. So they can frack without using a fluid.
That's cool.
And that,
this is
that
an
could
example.
be used for getting steam out too.
Yes. This is thank you for that. This is a slightly different one. It's a rotating drill, but it also hammers. And you can see it has those tips there. So you can be pounding as well as twisting, and they call that percussive drilling. And they feel that they can go a lot faster and more inexpensively with these special percussive drills. What you talk about is also any interesting. I hadn't heard about microwaves being used, but you'd have to have a lot of microwave energy to pierce rock. I've used microwaves to heat up cancers, and that's very different from heating up rocks. So you need a lot of power. You quoted as equivalent to a lot of microwave ovens. How many microwave ovens did you say?
I lost the page here.
I thought it was 500. Did you say
500?
Yeah,
500.
Yeah, you'd need a lot of microwaves to tear apart rock. Microwaves tend to bounce off of things, but with the water medium there, it would help the microwaves transmit through the water, and
that's interesting.
That's interesting.
The whole thing with fracking though is pressure. You've got to have whatever the fluid is, good or bad. It's that pressure that they're pounding the rock with to frack it, isn't it?
Well, the initial fracking is, if you look at what is shown in the slide there, it looks like there's sideways pressure for the percussive drilling. In a regular fracking, the center there would be an explosive, and the outside is a cement sheath, and the explosive is set off, and the cement outside perforates the rock around it. So it's kind of like setting off a bomb at the bottom of the well.
But my point is, these pumps that pump the fluid, they're really creating pressure that it's like hydraulic. It's a hydraulic pressure. It fractures the different planes of the rock, as it goes. So there's different ways you can do it.
Right.
We've got 3 different ways at least here that they can do this stuff, right?
Yes.
Yeah, that's good. Thank you for bringing that up. It was good timing. Just worked right in with this percussive drilling. Now, people are trying to cut the cost. I don't fully understand this graph, but basically, this is business as usual, of course. And they're trying to get rid of exploration fees. I'm not quite sure. They said they were reductions from previous, and that's all they say. But they may, I think, that by going back and perhaps finding abandoned wells, they can avoid the cost of exploring and drilling and exploration. They might be able to cut some other costs here. And so they have this word earth shot. I've heard that word before. I don't know exactly what it means, but I think it relates to some terms in Washington where they want to make costs support for non-fossil fuel, cleaner sources of energy. So it's just a projection of how they might cut costs, and they're starting off with 30,000 and working down to less than 5,000. So they're talking about a 6-fold reduction in cost is how they think they might do it. So, beyond that, I have not gone further. This comes from our famous NREAL, and I'm amazed at some of the projections. Here we are down here halfway between 2020 and 2030. Well, not even quite halfway. We're just starting 2024 pretty soon. But you can see if you follow the color code, geothermal is down there, and it's sort of they're talking about it maybe picking up around 2030, and they're talking here of significant increases from what we were projecting as a 0.5%. This looks like it's up to a good 10% or more from geothermal. But I couldn't help but looking at these other sources of energy that they're projecting by 2050. It almost makes me laugh. They have nuclear as shrinking a little bit. And then they have coal. Coal is seen here, and it just kind of wimps out by 2030. Lots of luck, fellas. I love to see it go. Then they have natural gas combined cycle. And for some reason or other, that just sort of pretty much goes down to a whimper and stays going until 2050, but it's part of the fossil fuel story. Then they've got natural gas CT, and they go to biopower, which is all pretty stable. And look at this baby blue onshore wind. Woo! That more than doubles over the next 10 years, according to their projections, and continues with that as some other things help to boost them. And then similarly, this way more than doubles photovoltaic. You would think photovoltaic was just the next best thing on the planet to look at that curve. This is comparison of energy generated. And of course, it's no wonder that an association of renewable energy are making these projections.
Oh,
but I'm just putting.
Before you leave that slide, Richard, can I just make a comment? Yeah.
Yeah, I'm going to go back to it. But anyway,
didn't you? Did this come from NREL, National Renewable Energy Lab? The title tells you their bias. They are all about renewable energy, and that's their bias, and they're gonna inflate the hell out of it. Okay, that's my point.
Sure. I agree with your point completely, and that's why I'm saying I originally collected this information because I was looking to see if they agreed with what I've been researching before, and that was that geothermal has a bright future. And then once I saw the graph, I thought, well, here's a whole key of other sources. Let's see what they've done with the other sources. And I got to these two, and I kind of laughed. You're absolutely right. The bias is extreme. One would think that they've never seen this before. This comes from our own Department of Energy quadrennial review. And look at the different amounts of cement, concrete, glass, steel that are used to make the amount of tons per terawatt hour. And you're talking 16,000 tons per terawatt hour. And you compare that with nuclear, it's about
20 times.
Yeah, 20 times at least less. That's correct. And so, I put the slide in because it does show geothermal. At least it's not as bad as photovoltaic. But and this is just for the terawatt hours, tons per terawatt hour. That does not take into account the longevity. Here, the longevity of photovoltaic and onshore wind, we know might be extended in some cases from 20 to 30 years, but nuclear is going up to 80 years routine. We haven't got to the end of that necessarily. And so that's not to account here, nor is the area. Go ahead.
The other point is every 24 hours, you have to replace the solar photovoltaic with some other source. The sun goes down every 24 hours.
Yeah, that's written right here. Wind is 11 times nuclear, solar 18 times, must be replaced every terawatt hour. That has to do with the durability. So yeah, that slide barely relates to my topic of geothermal, but it just does point out that at least it's clean, it's non-radioactive, it doesn't scare people, and hopefully they don't disrupt the rock with too much fracturing. But I thought it was interesting to compare. And this is the other ones were the generated. This is capacities. The capacities are even wilder, and they seem to think that these batteries are going to just they're going to increase the capacity, I suppose, but it's not a source of energy. So it just shows the how you have to be careful how you gather your data. Okay, we're wrapping it up, but I wanted to mention another aspect of geothermal energy, and that is that it can enhance pumped hydropower. You can sometimes use that energy from geothermal plants to raise water to a higher level and then use it as it's going down the shaft. Our friend Brent Rich, some of us know, who has been working with the Dairyland Power with a considerable amount of nuclear experience, is interested in getting involved with NuScale. And I think he's getting a little frustrated with the amount of time it's taking, because he's now gotten interested in geothermal energy and how it can be used to enhance hydropower there along the Mississippi River Valley. I'm not sure where that's going, but at least it's something for him to get involved in while he's waiting for NuScale and our regulators in this country. But it's just a thought. I didn't go into this in depth, but it would be a way to store renewable energy, and they're looking at old mines, and that's what they're doing. What Brent Ridge is doing, he's looking at old mines that are abandoned and finding ways to use various sources of energy to enhance stored hydro. So I come to the last slide. I built an airplane a long time ago, and so my heart goes into this cartoon a little bit. You see two guys on a desert island. They've cut down all the trees except one. Not only do they have no space for a runway, but they don't have any
motor
flotation in case the runway runs out, and they don't have a motor. Of course, they're looking in the nose. So the one guy says to the other, "Now comes the hard part." And the title of the slide is, "Our task is to scale up to realism." And those last slides on the estimated costs do need to scale up to realism. So I couldn't resist this one just for fun. So we are at just at 11:15, and you've been a great group. I really appreciate the comments and questions, because they fit in perfectly to the presentation and allow me to elaborate and have brief discussions with you, and it enhances the talk a lot. Thank you all for coming. Any other thoughts? We've got a little bit more time here.
Well,
lots more.
going back to the beginning of
Yep.
what we're talking about here,
Yep.
I don't know how many of you recall Project Plowshare. That was drilling a hole, putting an atomic bomb basically down the bottom and exploding it and seeing, first of all, what we could get out of it. And there were some follow-ups to that. But in most cases, or in all cases, I should say, when you pump something down, it came up with too much radioactivity in it. So those areas were shut down. And I just thought I'd bring that up.
Yeah, that's interesting. I've heard the term, but I didn't know the results of that those experiments. I think there was a that helped to lead the public negativism against nuclear energy, wouldn't you say? Because
I think it was.
Yeah.
I think it was. Well, there was a push to try and take the edge off the atomic bomb being destructive and try and look at areas where it could be producing something useful to society rather than destructive. Project Gas Buggy was also one of those underground. They tried a lot of different things.
wasn't Eisenhower instrumental in that project?
I don't know, but there was also talk of a ocean level Panama Canal by doing a series of atomic bombs under the land to cause the mountains to just sink down below sea level. You make a big hole in the ground underneath and the top collapses.
What would that do? I mean,
that would connect the Atlantic and Pacific at sea level.
Oh, I see what you're saying. Yeah, okay.
Yeah, that's pretty wild thinking.
Yeah, I think.
You guys have you been through the Panama Canal?
I have not, but I watched my son go through.
Okay.
Yeah,
I think it's wonderful to see how we've used locks to in a natural system, some natural systems with some connections. It's a wonderful feat of using nature and ingenuity to connect two big oceans like that. So
they're having a problem this year with lower rainfall.
Yeah.
Yeah.
Well, hey, I've got a point I wouldn't mind making with the enhanced systems.
Yes.
And that they're a closed system, and when you have a closed system, it seems like cooling towers should be used. It gets rid of water vapor, but it cools down the water so that it can pick up more heat. I don't know, down below, how far deep, if it's 8 or 9 miles or whatever, how deep they have to go. But the cooling tower, but then some of these systems are trying to eliminate that, but they're not as robust. So I don't know if there's a connection with that.
They're not as big. In Bavaria, there are a lot of beautiful forests that you saw in that photograph, and they've disrupted the forest very little with this geothermal unit. I would be interested to know, a colleague of mine who's listening in, Jim Caldwell, gave me this clue that Alberta, with a huge history of petrol know-how, were consulted and are having a good relationship with the Bavarians in perfecting and fine-tuning this work. But they seem very happy with the idea that they can reduce costs and keep it fairly small. As you saw, I think it was 8 megawatts, if I remember. That's equivalent to about eight windmills, 8 wind turbines. And but the other thing is that's just capacity. The fact that these closed loop plants should be lasting, 80 or more years, maybe 100 years or more, and rather than 20. And also, they're not intermittent. This is around the clock. And so I think that by cutting costs and eliminating the big pool, as well as some of the cooling towers and so on, that they can just have a closed loop, which they find very efficient. And I don't know the details of it, but I was pleased to read a bit about it, and that I would like to read more about it. I think it's might be a very useful way for geothermal, rather than increasing the size per unit, just have units that are very self-contained, not intrusive. Maybe Japan would accept those more likely into their culture, and just go by small units. 8 megawatts is not a bad amount of energy. I compare it to
figure per megawatt is 1,000 homes per megawatt. That's
right.
Powering. But when you got to go so deep to drill, that seems
true.
to be an issue too.
Yeah.
That's my point.
Yeah. Well, they have the one vertical and a whole bunch of offshoots, but I'm not sure the details of that. Yeah. But yeah, it'll be something to watch. But anyway, I think it's I enjoyed working on this. I've been wondering for a long time, when we started 12 years ago or so, each one of us in this little Pathways to a Sustainable Planet would grab a topic, and some of those people might well be still in the audience, Tom Newman and others, Paul Brendel, and we've been not really touching very much on geothermal since then. We've always said, well, geothermal is pretty small, less than 1%, but now it might have a chance to jump out into the public in a good way. So I found it fun to research this and learn a bit more about it. I want to invite all of you to do that also, and I appreciate many of the speakers that we have this fall, and to chip in. We've got some new speakers. Steve Shellen, of course, from a background in nuclear, is going to talk next week on insights for assessing radiation risk. Merck Corwin, we've heard before. He gave us a really good talk, if I remember correctly, on methane. And he's going to talk about artificial intelligence and GAI. So that's going to be challenging. We hear a lot about that today, and it would be nice to get his perspective. And Alan Pentikoff is a real big enthusiast on electric vehicles. He'll be talking November the 20th. And then I'll talk on a very touchy subject of overpopulation on the 27th. So we've got lots of members of Friends of Fission and other people who are outside of that, people like Mert, who are very happy to research some of these things. And I'd be glad to hear from more of you so that we can develop a good program for next spring.
I've got one
Richard,
comment quick.
Can I jump in and make a comment? This is Joseph Talmadge. So look, first of all, let me say that was a fantastic talk, and I really appreciate the insight that you provided in these slides. I really want to commend you for giving this talk. It was really excellent. I just want to comment about two things that were said. So first of all, you mentioned the GeoVision report. So I wanted to comment first about that, which is, this is a report that came out from the Department of Energy in 2019. It was a combination of people from academia, from industry, from federal institutions, and so the Department of Energy put together this panel to try to understand what the prospects are for geothermal. And in this report, you can read the fact that within the United States itself, there's the potential for having up to 5 terawatts of power just from geothermal. And in this report, they speculated that you could have perhaps an increase in geothermal in the United States by factors of like 26 or so, which was comparable to what your factor of 50 was. But this is from the GeoVision report. The one thing I would point out too is that if you dig down far enough and you get the temperature of water down to like 300, up to 370, I think it is, C, and pressures of like 3,000 PSI, then the water goes into a state where it becomes supercritical. And at that point, the amount of the energy density of the water goes up by factors of 10. And that leads me to the next point that I had heard of that I wanted to pick up on, which is the concept of using millimeter waves for drilling rock. So this is actually an extremely interesting idea. And to some extent, it's an outgrowth of the fusion community. So there's a company called Quaise out of MIT, which has been a leader in development of millimeter waves for many decades. And so if you look up quaise.com on the internet, you can see that their prospects of using millimeter waves for intense drilling, you know, like we're talking about 5 to 10 kilometers down, so you can reach that supercritical water. And their prospects are, if you look on the website, they want to get to, they think they're going to get the first plant up by 2026 or so, where they can reach this sort of supercritical water. I would say, first of all, that any claim that you read from private companies out of the fusion industry has to be taken with a huge dose of salt. But these are reputable people. These are not just some, these are people who've worked in this field for a long time. So the timeline may be completely unrealistic, but the research is actually interesting and important. So those are the two things I wanted to comment on. And again, thank you so much for a very interesting presentation.
Well, you're very welcome, and thank you for your comments. Would you please repeat the spelling of Quaise for me to make sure I have it down?
Quaise. Just look Quaise.com, so you'll see it's an offshoot of MIT. And
Quaise. Quaise.
Quaise.
ISE. Okay. Very good.
Yeah, so it's just an interesting feature that aware, but the point that hadn't been brought up, I thought, is the concept of trying to reach the supercritical water, where the energy just really skyrockets, and that's the interesting feature, I think, as to where enhanced geothermal might go. And again, this is an offshoot of the fusion community.
Right.
So there's some credibility to it, but we'll see what they can come up with.
I would suggest that those pressures and temperatures absolutely need cooling towers to make it thermally efficient. I mean, thermodynamically efficient. That's just my 2 cents.
And you're talking compression pressures that challenge material strength.
Yeah.
If you look at
that's true. Well,
if you look at the earth hole that Russia drilled, they eventually stopped because of the fact that they couldn't drill fast enough to offset the creep of the sidewalls closing out the hole. You get far enough down in the earth and the pressure is so tremendous that even drilling a small hole, it closes in on itself from the side pressure.
Yeah, I read about that too. They got so scared, they said they thought there was hell down there.
Yeah.
They just covered it up and forgot about it. They didn't want to think about it again.
Well, how deep was that? How deep was that they were drilling?
I've forgotten, but it's deeper than anybody's ever gone, right?
Yes, it started as a consortium, and everybody dropped out, and Russia continued. And you can Google it. It's very accessible. One other thing, I'm sending out to the Friends of Fission, because I don't have other links, so you can forward this, Richard. Remember the first time Colorado tried fracking with a nuclear bomb? Here's the history.
Yeah.
And it's got a number of things that somewhat apply to probing the earth to get energy or creating a source of energy that can be extracted from the earth. So
You can give us that material next week. How's that?
okay.
You can incorporate it in your talk next week. I'm really looking forward to all these talks that are coming up. Radiation risk is really something we need to get out to the public. Artificial intelligence also. I mean, we've got some really good topics coming up. And as I look at what we just have been reading and thinking about this morning, it makes me realize that we're just on the brim of I think a whole new field of geothermal. Who knows if we were to repeat this talk in 5 years' time, where we would be going. We've dealt with history over the past 100 years, and where are we going in the next 5 or 10? It could be pretty steady, as I showed in some of the slides, or it could be much faster than we even imagined. So I was going to talk about that Russian hole, but I don't go to the slides. But that's a fascinating subject too. Yeah.
I think the point is that because the Earth is so varied all around, there's not going to be one source of energy that's going to be suitable for every place, be it nuclear, geothermal, solar, wind, water. Some of it just is impossible to fit into the situation where people have built civilizations.
Yeah. You remind me of a TV program I saw about 5 years ago of an island off of the west coast of Scotland. And they wanted some electricity for charging up their cell phones and so on. So they built a windmill, and that didn't work out very well. The winds were pretty bad. So they put up some solar panels, and they've got a system now where they're very content. They have a few tourists come now and again, but not too many. And they have just enough electricity at certain times of the day when the sun is shining, and they've adapted to it. And so when you have a happy society building its energy as needed, it can work out, and there are quite a variety of different sources. So
yeah, I think I came across that in the past.
Yeah, it's a cute story. But it's really fun, and I thank you, Joe, for your comments. Joe Talmadge. I think Joe is, if I remember correctly, has a lot of experience in the field of fusion, and appreciate your thoughts. And we'd love to hear from you one of these days, Joe, to bring us up to date in that area, maybe next spring. But it's fun to share ideas like this. This is what makes PLATO fun. There are 40 different chapters, and we just happen to be one of them that love to explore these ideas, and I look forward to them every week. So we'll call it there for today, and thanks all for coming, and we'll look forward to next Monday hearing from you, Stephen.
Yeah, I really enjoyed your slides. I'd like to see them again to look at them.
I can, they will be, it's been recorded and it'll be online with our comments, and then I have the slides, and I have sent them around to my son, who gave me some of the originals on the geysers in California, and so I know they will go on email. They're about 23 megabytes, I think. So if you want the slides anytime, let me know.
Yeah, I wonder if there's any radiation coming out of the Earth.
No, right. Doug Edwards sent his slides around, by the way, from last week, and I have those in case anybody would like them. I could easily forward them to you. So I'm sure that is also up on as a recording, but sometimes the slides are nice to look through. So
okay. Thank you.
Okay.
Bye.
Bye-bye. Thank you. Bye-bye.